419.10 Nuclear, Domain, and Elementality. Where the primitive polyhedron considered is the vector equilibrium, the closest packed sphere shell growth rate is governed by the formula 10f to the second power plus 2. Where the most primitive polyhedron is the tetrahedron, the growth rate is governed by the formula 2f squared plus 2. In the case of the octahedron and cube, see section 223. So if you go to a 2 or 3 frequency tetrahedron, then you would put that frequency to the second power. So I guess 3 to the second power is 9, 2 times 9 is 18 plus 2, and it would take 20 balls to make a tetrahedron. The formula is reliably predictable in the identification of the chemical elements and their respective neutron inventories for each shell. The identifications are related exclusively to the unique nuclear domain pattern involvements. Fuller is deeply convinced that some series of numbers in the periodic table relates to these stacking numbers. Fuller's not just matching number to number. He's saying or theorizing that the reason why the numbers are so significant and that at 92 is the end of the regenerative elements, it being over here, is because there's an underlying tetrahedral symmetry at work.
Yeah, I'd like to make a comment that, or a clarification that the 10F2 plus 2 is the outer shell, not the total number of spheres in that frequency. So as you're like with the tetrahedron 2F squared plus 2, if you start with, well, that's interesting with the tetrahedron because you're having a central ball represent a whole tetrahedron. It's kind of counterintuitive. And as we talked about a couple of times ago, there are several like iterations of a tetrahedron before you get a nucleus. So the second wave of a tetrahedron, the second frequency shell, the first frequency shell would just be, it would be 4. So that would be a non-nucleated tetrahedron to start with. The frequency being 1 means the gap between the spheres. There's one gap between two spheres, right?
So I'm not understanding, because here's a frequency of 1, and as you said, 2 times 1 is 2, 2 is 4, and there are 4 balls.
Yeah, 1 squared is 1 times 2, right?
Which is
Plus
2.
2,
Plus
yeah.
2. But
So
now when we go to
yeah.
2 frequency, and I'm adding on 6 balls, so there's a total of 10 balls. So 2 also works, right? 2 times 2 to the second is 8, plus 2 is 10, right? So then there are 10 total now, right? 3, 4, 5, 6, 7, 8, 9, 10.
So that's a total number. Okay, so that's a total number of spheres, but there's no nucleus.
Right, there's no inside. Yeah, so
Right.
they're all on the surface.
So
now things get interesting on the next one. So these are all triangular numbers. So this is 4, 7, 8, 9, 10. Now I'm adding 10 to 10, so it's going to become 20. There's still not a ball in the middle.
There's the red one, yeah.
It's still nothing in the middle. So let's try the formula. 3 to the second power is 9. 2 times 9 is 18, plus 2 is 20. And all 20 of these are on the outside. Now comes the exciting moment. That's why I call this one red, because it's going to get eaten. Here's a new triangular number, 15. So how many did we have here? So I add to the 20. This was 20. And now I'm going to add to the 20, 15. So that's 35 total.
You got a 4 frequency tet there, right? 1, 2, 3, 4. Yep. So 4 squared, 16 times 2, 32, plus 2 is 34.
34. And there are 35 balls. So the formula works. When we added this one, we created a centroid, which you can see because we colored it red right there.
Yeah, and I think it's a little more a little more obvious when you're doing a vector equilibrium that he's talking about shells rather than total spheres.
I was surprised by his use of primitive. Instead of saying the simplest or the basic or the fundamental, the primitive polyhedron in both occasions there. Yeah, just
Yeah.
struck me as odd that he chose that word. But
I'd comment on the primitive that he was probably talking about, the root word being prime, also to do with like a mathematical understanding that it's a geometric equivalent of a prime number.
419.12. When a new nucleus becomes completely surrounded by two layers, then the exclusively unique pattern surroundment of the first nucleus is terminated. Thereafter, at 3 enclosure levels or more, the initial nucleus is no longer the unique nucleus. The word elemental relates to the original unique patterning around any one nucleus of closest packed spheres. When we get beyond the original unique patterning, we find the patternings repeating themselves, and we enter into the more complex structurings of the molecular world. So you have a nucleus ball. For example, in the model that I was showing, there was a red nucleus ball. And then you have a shell around that. Now, if we add another shell around that, then somehow the shell, the original wrapping one, is also nucleated. Okay, 419.13. Uranium-92 is the limit case of what we call inherently self-regenerative chemical elements. Beyond these, we get into demonstrations of non-self-regenerative elements with the split-second life of negative universe. These demonstrations are similar to having a rubber ball with a hole in its skin and stretching the hole's rubber outwardly around the hole until we can see the markings on the inner skin that correspond to the markings on the outer skin. When we release the ball, the momentarily outwardly displayed markings on the inside will quickly resume their internal positions. And those who read the last section found the same story about a rubber glove. And finally, as we see in section 624, the inside outing of universe occurs only at the tetrahedral level. In the nucleated tetrahedral closest packed sphere shell growth rates, the outward layer sphere count increases as frequency to the second power times 2 plus 2, with the outer layer always doubled in value. See how this vertex, if you push, of course the sticks would have to be a little flexible, but you move through the other face. You can move straight through. So Fuller does consistently and often talk about inside outing a tetrahedron, while every other Platonic solid does not have a vertex against a window. So you can't do that. In this drawing, you can see it pretty well. Every other shape, a vertex is against a vertex, not against a window. So you can't inside out these things in Fuller's approach, only tetrahedron.
So we're taking the vertex and pushing it through a window so it comes out on the other side.
It goes straight through. With the others,
Yeah.
it would be quite a contortion to pull it. But more